Hey there, I'm Rodolfo, and in this video I'll be presenting what I worked on this past semester at their project, in which I implemented SLAM using a 2D LiDAR scan in a Highwonder Jet Auto bot, of which I'll be showing pictures and a video later. So this is the agenda for the presentation. Let's get right into it. First, let's get started by understanding the task and the motivation behind it. I said that I implemented SLAM, simultaneous localization and mapping, which is critical for autonomous driving. It basically allows bots to map and move around or map and navigate while also keeping track of their position. Since it is an essential task for autonomous systems like self-driving vehicles, it seemed appropriate to set this as a project for an autonomous intelligence robots class. However, there is also a second motivation behind it, and that's that my PhD advisors recently published a paper on a new approach to machine perception during motion, which basically allows to perform certain 3D mappings and getting the camera location with only a sequence of 2D images, no stereo cameras. Yeah, the method is new, but there are not that many studies that actually compare that with other standard approaches. So hopefully this project will evolve and serve as a baseline that I can use it to compare it with this new approach in tasks like obstacle avoidance, for example. But okay, let's get back to this project. And let's understand the task, let's understand the constraints and the assumptions. I am working with a Highwonder Jet Auto Pro. That's a 4-wheel bot with a LiDAR scan, a robotic arm, and a camera. And it is computationally powered by a Jetson Nano, but it is an older generation. So it uses ROS1 and Ubuntu 18. Also, the camera and the robotic arm remain offline for this project. The final implementation only uses the LiDAR scan and the wheels. Now, the proposal initially had two sets of tasks. The first set is actually described here, and the second set actually built on the first one by just changing how the mapping works. Instead of running the algorithm and manually driving the vehicle, it will autonomously explore the area using AR tags. However, that was only going to be the case if time allowed, and time didn't allow. So let's focus on the first set of tasks, okay? The first set is a 2-part task. Part 1 is about mapping, and basically I run a SLAM algorithm, of which I'll be talking later, and I drive the bot manually around the room. The second part basically loads the map that I generated in part 1 and configures some initial pose of the bot, which is the location and direction, and then I can select certain points on the map for the robot to navigate to them autonomously. That's the goal. Any constraints? Yes, I'll be using only the wheels and the LiDAR, and I will be operating, of course, within ROS1 and Ubuntu 18. Any assumptions? Yes, I can use any ROS built-in tools or commands, and I can also use other files provided by the manufacturer. With that in mind, let's get into the implementation details and demonstration. Briefly though, I would like to talk about my communication setup, because this is a robotic project, and it's common in robotics projects for bots to broadcast their own Wi-Fi without being connected to the internet. And also, I was working with a Mac computer to make my life a little bit easier and be able to connect to the bot and also connect to the internet. I added certain intermediaries between the two. On the first stages, I configure a Raspberry Pi that you can see on the top right, which basically took connections from the internet through a domain that I set up, and it also had a secondary network interface, the antenna you can see, that connected to the bot. So that means that I could use the Pi as a proxy when I was away from home to connect to the bot directly. On later stages, when I actually wanted to pull up some ROS visual tools, for example, what I did is that I built a virtual machine with Ubuntu 18, ROS1, and connected it through the USB Wi-Fi dongle that you can see on the bottom left to the robot. Great. In both scenarios, I could quickly switch between sending commands to the bot and opening tabs to investigate why a certain error happens. Meaning I was basically making mistakes at the speed of light, right? But okay, the communication was set up. I had my, in days after configuring the bot, these are the steps that I use for generating the map. I did end up using a launch file provided by the manufacturer, but my bot is not new and it wasn't exactly in perfect conditions. I started by using Gmapping at the Gmapping package that you can see there, but the way that one works is that it generates a map by combining the LiDAR scan and the wheel's odometry. Unfortunately though, my bot had one wheel and now two that have screw holes stripped. In other words, the controller will send a command to move forwards, the motors will move, but the wheels will stay static. Then I moved to EctorSlam, which is basically a similar mapping algorithm, but instead it only relies on the LiDAR scan. It allowed me to get much more accurate mappings, even when the robot was like slightly shifting to the left, under one condition though: I must drive slow. And that's because the way it works is that it stitches together different scans that have enough overlap. So driving slow, I will give it enough overlap. That's the goal. See. After that, I basically saved the map using the map server node, which you can see at the end. Task 1 completed. You can see the generated map on the left and some pictures of the room on the right, and that's a long hallway, so it was very accurate. Part 2 of the second part of the tasks, it was about loading the map that I generated in part 1 and allowing the bot to move autonomously. Again, I did use a launch file provided by the manufacturer, which basically took the map that I generated in the first part as an argument. And in my computer, I ran ROS Visualizer and a ROS Qt based GUI reconfigure tool, RQT reconfigure. Let's say that the first attempt didn't fail, but it did aggressively manage my expectations for the rest of the project. But okay, I was able to set up ROS Arvis. You can see a screenshot of it on the right. I had to configure the map, the laser scan, and an estimate to the pose. And with that information, the bot was ready to pick any or navigate to any 2D goal that I set it. Additionally, I had to configure other parameters of the algorithm, like the maximum speed or maybe the distrusting of the odometry while it was navigating. And for that, I used the RQT reconfigure tool, which you can see a screenshot of it on the left. The bot navigated using the adaptive Monte Carlo localization. That's how I kept track of its position, and using the Dijkstra algorithm for global mapping and to get to the goal. It also kept a local cost map, basically to avoid any threats or also adapt to small changes in the environment. Now, these are not specific parameters that I set, but I read that these are the defaults in the packages that I use. Great. If you're watching this video on my website, you will probably find a demonstration right below it. If you're watching it on YouTube, you can probably find the video demonstration on a link on the description. The demonstration doesn't have any audio, but basically shows how I run the commands for running the SLAM, navigating the bot, saving the map, and then loading the map to make it run autonomously. All the steps, really quick. Okay, what resources I use? I use ROS Melodic wiki documentation, which was essential for understanding certain packages, how they worked, what are the requirements. I had to navigate through the manufacturer provided files like the source code because I couldn't find much documentation, but the source code was easy to read and find what arguments actually needed, for example. And Google Gemini because it was great to ask it, hey, why is it doing that at 2 in the morning? I documented the project in my personal website. You can find the link here. And I also created an open source repository where I documented any major steps and any important findings because I wanted to make it easy for me to document everything much better at the end, and also because I'll be working on this bot in the next semester for future research. Finally, did it execute the proposed functionality? Yes, it was successful. Any limitation and areas of improvement? Many. However, I list a few here. I want to be able to change the first part on how it navigates so that I don't have to manually drive it, but it could explore autonomously. I want to update the software, although that might not be possible with this specific bot due to drivers, and replace those loose wheels, which I think I'm getting the replacement today. But I recall that I'll be working on this in the next semester, and in future research I'll be probably changing stuff and adding things in the future. And that's all, folks. If you have any questions or want to engage, please do so. Depending on the platform you're on, you'll probably have comments or other ways to engage. Thank you again.